So thanks for the introduction, and thanks more generally to the organizers for inviting me to come and lecture here. So this lecture is going to, as it says, be on the proper orthogonal decomposition. And I want to look at it from a few different directions, but really focus on, one, how we compute the POD in practice, and two, how do we interpret what it actually means or what it actually gives us. So POD is perhaps one of the most ubiquitous data-driven modeling methods and most classical data-driven modeling methods in fluid mechanics, and underlying mathematics is used in many other fields, often called different names. It's undergone many different formulations and variants over the years, which has been a function of the types of things that we can do and the types of data which is collected in fluids. And I'll speak about that a little bit more specifically later in the lecture. But as I said before, really this lecture is going to provide an introduction to the main ideas, the underlying mathematics, and how the POD can be computed in practice. So what are we really trying to do here? So some of these ideas have been talked about in the first two lectures, but basically we're going to assume that we have some function or some data that is a function of both space and time. So it could come from some underlying partial differential equation, but more generally it's just a data set. And so the idea here is that we want to take this data and, using the data itself, decompose the data into some sense of fundamental building blocks. And again, this is a simple example that will go, one-dimensional example that we'll actually study in this lecture, but of course we're often more interested in fluid systems where one can look at a simple oscillator type system, so similar to what Professor Nowak was talking about in the first lecture today. But things can very quickly get much more complicated, so such as the turbulent systems that Professor Jimenez was talking about. But one point that I want to make is that you don't have to add too much complexity to your geometry to start to get dynamics that are perhaps more difficult to understand just by looking at a visualization of the data. And so that, again, motivates a perhaps more formal or rigorous way to be able to study systems from looking at the data. So this is just flow past two block bodies rather than one. So what are we looking at here? So as I said before, we have a function, or we have data which is a function of both space and time. Though for now, I'm not necessarily saying anything about whether we're resolved in space and time. And the types of questions that perhaps we're interested in asking is, how can we start to, in a rigorous way, understand what features are present in our data? Moreover, perhaps this same method could be used to efficiently store or manipulate our data. And then furthermore, this could be used perhaps for the identification of reduced order models, such as what Professor Nowak was talking about in the first lecture today. But really, the underlying principle behind what we're trying to do is do nothing more than a separation of variables. So we have data in both space and time, and we want to represent or approximate that data as a function of space multiplied by a function of time, or some sum of these. So this is no different from perhaps the first method that you try when you are solving a PDE. So how do we come up with such a decomposition? Well, it's obviously not unique. There's a lot of different ways that we can do such a separation of variables. If we didn't have any data, then maybe we could use analytic functions like Fourier transforms or other sorts of transforms to do so. But with data, or given access to data, there are things that we might ask, or properties that we might ask for this decomposition to possess. And perhaps most obviously, it's reasonable to want this decomposition to be efficient. in the sense that you don't need many terms to get a good approximation for your entire data set, and then hopefully your entire system that generates the data. And really, finding a decomposition which is optimal in this sense is what the POD does. And again, as I mentioned before, there are different variants of the POD that sort of add tweaks to this, or how you come up with these terms, or whether some space and time can enter into sort of both of your functions. But broadly speaking, you're trying to solve some sort of optimization problem that gives you, in some sense, the best representation of your data. So what I'm going to do is jump straight into sort of the more definition of POD in practical terms. So that is as a property of some data set that you have. Later on, we'll talk about perhaps a more fundamental definition in terms of sort of the properties of our underlying continuous functions from which we sample the data. But for now, we're going to assume that we collect some data at some spatial locations and some temporal locations. And as I said before, we're not necessarily saying anything about whether we're resolved in space or time. So the first step, and again, there are multiple ways in which one can compute this decomposition, but I'll go through sort of a common way to do so, is to arrange the data into one big two-dimensional array or matrix. And we're doing this such that the row index indicates our position in space, and the column index indicates our position in time. So again, the assumption we're making here is that we're always sampling the same points in space at every time. There are ways around this if you don't necessarily have that data, but that's sort of the only real assumption that we're making about our spatio-temporal data, is that we can assemble this matrix. Okay, just to provide a few more generalizations. And again, I'm going to kind of go through a few relatively simple steps, but things that are perhaps skipped over when you read about POD or other methods in papers. So I'll try to be fairly explicit about how we actually do these steps. So for example, if we're measuring vector quantities, then we have, in the case where we have perhaps a two-dimensional velocity field, we have two measurements at every point in space. All we need to do then is just stack those two measurements again in the one column. So still we have every column within our matrix is just all of the stuff that we measure at a given time. And the same principle applies if your spatial dimension is more than just 1D. So most typically your measurements in space are in a two-dimensional or three-dimensional space. You don't do anything different there. It's just that this x is sort of a vector of your spatial coordinates. So again, this is sort of an obvious thing to do. It also doesn't matter whether we list u and v for a given location next to each other in this matrix, or if we do it this way. It really makes no difference to the outcome as long as we're consistent. Okay, so what are we trying to do? So now that we've sort of matrixified our data, the equivalent to asking for that separation of variables is asking for a decomposition of this matrix, which looks something like this. So the way that we've arranged the data in our matrix, with columns corresponding to all the measurements at a given time, and rows corresponding to all measurements at a given location, or all measurements of a given quantity at a given location, then what we end up looking for is a factorization of this data matrix such that we have a vector on the left, which is only going to be a function of space, and a vector on the right, which is only going to be a function of time. And the idea here is that we hope to be able to do this in sort of a low-rank way. So that is, the rank of this matrix on the right is going to be at most either the number of columns of U, or equivalently the number of rows of A. So how do we do this? Well, we use a singular value decomposition. So, and I'll speak a little bit more about what this is. Just out of interest, who feels completely comfortable with an SVD or knowing what it is? Okay, good. So maybe half the people. So I'll go through this relatively quickly, but I'll explain what an SVD is and what properties it has. And more importantly, why that's useful for satisfying the desires of what we're trying to do here. So an SVD actually comes in a few different variants. We can start with the full singular value decomposition, where we can express any general matrix as the multiplication of these three operators, where the special thing is that the U and the V matrices are unitary. So that means that both the rows and the columns of the matrix are orthonormal. And sigma is a diagonal matrix, or a matrix whose main diagonal are the only non-zero elements. And moreover, those elements are non-negative and decreasing from the top left entry down. So this factorization always exists for any matrix. So it's not like an eigendecomposition, which you can only really apply to square matrices, and that where sometimes you don't have a full basis of eigenvectors. The SVD can be applied to any matrix. And is also unique modulo some rotations on U and V. And for now, we can think about this star, which is the adjoint, as a transpose or conjugate transpose if you have complex data. But I want to leave it a little bit more general for reasons that I'll talk about later on. Okay, but that hasn't really done us any good so far, because this is still a square matrix which, if n is bigger than m, is larger than our initial data set. So we've kind of gone backwards. So what can we do? Well, we have more information that we need, so we can actually cut out all the stuff that isn't actually useful at all. So by truncating, in this case, columns of U corresponding to entirely, sort of zero rows in our sigma, we don't lose any information, but we have a more efficient representation of our SVD. So all that we've done is simplify things a little bit. And also, if Y was different shapes, so if it was wide and short, then we'd be cutting out from V rather than from U. Okay. The other thing to note is that here U is no longer going to be unitary. So U star U is still the identity, but not UU star. But we can actually go further than this. So using the fact that sigma has decreasing entries along its diagonal, we can actually start to cut out some of these lower ones, which are going to be small, and so reasonably are not going to contribute too much to the overall representation of our original matrix. So we can produce what we call a truncated SVD, which is basically what we had started with previously, but where we cut out more rows of U and V. So there should be a star there, I realized. That should be VR star. And rows and columns of sigma. And why do we do this? Or why are we interested in SVD in the first place? It's because this actually gives us the best possible rank R approximation to Y. Or in other words, to write that more formally, in terms of best, we mean that if we take the Frobenius norm of the difference between Y and a low-dimensional approximation, or a rank R approximation of Y, then the optimal, in the sense of minimizing this difference, is given by the rank R truncated SVD of Y. So this is kind of, we've sort of gone to the side to just talk about some basic linear algebra, but that is really where all of the properties of the POD are derived from. So how is this useful? Well, to kind of go back to our original sort of summation notation, we have this approximation of our data set, which is obtained from a truncated SVD. Now we can write that as a sum of rank 1 matrices in this way, where uj and vj are the columns of u and v. And sigma j is the associated singular value. So all this is really doing is just expanding out our matrix product that we have up here, which is simple because sigma is a diagonal matrix. So what is this doing? Well, this, if we go back and look in more concrete terms about how we arranged our data, what this leaves us with is our matrix Y, which we can think of as a function of space and time, as being able to be represented in this way, or approximated in this way, if we're using just a truncated set of left and right singular vectors. And because of how we arranged our data, our left singular vectors, so that is the columns of the U matrix in our SVD, are only a function of space, and the columns of V, or equivalently the rows of V star, are only a function of time. So this has given us a separation of variables of our spatiotemporal data. And moreover, it's done so in a way which is optimal in a sense of what we were looking for. So we were looking for a summation that approximated our data with a small number of terms in that sum. And so the SVD of our matrix, due to the definition of the SVD and its properties, has given us precisely this. Are there any questions so far? All on track? Good. So what I wanted to do now was to go through an actual concrete example that can sort of describe or explicitly show how the SVD is computed. And I'm going to go back to this very simple data set that we looked at in one of the very early slides. And it's kind of a contrived data set. I've shown you here how it's generated. Apologies, there's a S2 that's been cut off. But basically, as you might have seen from intuition, some sense of, we have these two spatial functions which are localized in space approximately, that are Gaussians with different widths and different centroids, or centered at different spatial locations, that each are multiplied by some function of time, which here is just a sine wave. So again, we have one mode that oscillates at one frequency and one mode that oscillates at a different frequency. So what I wanted to do now was to explicitly show how we can compute this. And to do that, we're going to be using a Jupyter notebook. And so this, I believe, is now on the website, but there's also available at this link here. But you can also look at it after the lecture. So what we're doing is, to start with, just basically doing exactly what was seen in the on the slide. Can everyone, is this big enough for people to see up the back? Yeah, great. I could zoom in if not. So we define our spatial domain. We define the properties of our two bumps, if you like, so our two Gaussians. And then we formulate our spatiotemporal data by making an array, or two-dimensional array, or a matrix, where at each time we have the spatial modes multiplied by their temporal dynamics. See, so I can run this. Good. And if we wanted to look at what the component functions are, I'll run this again so that I'm sort of doing it in real time. They look something like this. So this is just visualizing those two component functions that I use to identify the data. That I use to generate the data, sorry. And if we like, we can visualize this in a different way. So this is just a visualization of what the data looks like as a function of space and time, which I realize now is sort of the transpose of what our matrix would look like, where space is on the y-axis and time's on the x-axis. Actually, no, I'm not going to try to live code. It's only going to end. It seems easy enough, but it's only going to end in tears. Just tilt your head to the side if you want to see what the matrix looks like. Okay, so how do we proceed? Well, we have our data matrix, and all we need to do is take the SVD. So regardless of what coding language or software package you're using, the SVD is one of the most ubiquitous built-in functions. So in the linear algebra subpackage of NumPy in Python. And so we can compute this. And note that here, I've said full matrices equals false, which is equivalent to, rather than computing the full SVD, computing the economy SVD. And so what that means is that in this case, we have more columns than rows. So U is a square matrix and V is a rectangular matrix. Okay. And actually, if I will do this one. If I said that equals true, then I end up with a square matrix for V also. Okay. So to start with, we can look at what our singular values are. So these S here denotes the diagonal entries of sigma. One other thing to note while I think of it is that, for example, if you compare how you compute the SVD between MATLAB and Python, if you're more familiar with MATLAB, it's basically the same, although Python by default outputs V transpose rather than V, or conjugate transpose. And also S here is sort of represented as a one-dimensional array rather than a matrix, sort of for efficiency. Okay, so the singular values. So perhaps unsurprisingly, given what we know about the simple synthetic data set that we've used, we have two big singular values that are quite large, and then a lot that are basically zero. And this sort of makes sense if you think about it, because we really have two spatial functions and two temporal functions, sort of two spatial functions, each with their own temporal functions. So you could kind of think about the data as being rank 2. And in fact, Y, the data matrix, is at least subject to a given truncation level, approximately rank 2. So this is good. So now let's look at what our singular vectors look like. And so our left singular vectors are our spatial functions, which are our POD modes. And they look something like this, which is nice, but is perhaps not ideally what we might have wanted, given what we know about how this data is assembled. In a sense that each of these POD modes is actually a combination of those two bumps that we use to construct our data. So we can still use these two modes to represent our data. It's just that they perhaps don't correspond to somewhat contrived modes that we use to generate it. And the reason why this is because the SVD is greedy, so it tries to put as much energy into the first mode as possible, which effectively means that we end up with a contribution of those two component functions. If we wanted to see that a different way, we can look at the mode coefficients, which are the corresponding temporal functions that tell you what your time evolving coefficients of each of your spatial modes are. And again, here we see that we end up with a mixture of a mixture of contributions from those two components. So from both of the frequencies. Okay, so are there any questions about what we're doing or how we implemented it or so forth? Okay, good. So this is a very simple example, but the methods that we used, or the code that we're using, wouldn't change too much regardless of what data you're trying to apply this to. Up to the limits of data sets that I can fit into memory here. Okay. So back to this example, which we've now done our POD on, and to look at things more visually, we have our full data, which we can represent as a sum. So these are those two terms in that sum, each of which is a spatial term multiplied by a temporal term, where we have mode 1, which is this guy, and mode 2, which is this guy. And again, as we saw with those plots in our code, each of which is a combination of both of these component functions, both in time and in space.